undirected graph, and your goal is to pick a subset of the edges, okay, so that their total weight is as small as possible and everybody is connected to everybody else. So that's the minimum spanning tree problem. And we said that there are two very simple greedy algorithms that that you can come up with. Okay, one is something that was just in class, which is you sort the edges in increasing order, okay, and you add edges at one at a time as long as the edge you are adding is not redundant. Okay, and this we said is called Kruskal's algorithm. This also turns out to be optimal. But we started analyzing a slightly different algorithm which had this intuition that, okay, your goal is to connect everybody, all the vertices to all the other vertices. Okay, so let's start building a connected component. So that's the idea behind this Prim's algorithm. We said you start with some one vertex, and you just add one edge at a time so that you grow the size of this connected component by one. Okay? And the edge you add is the one of the smallest weight. Okay, so formally this was that, and we said that the surprising fact is that both of these are optimal. They could result in different trees, but both will actually have the minimum cost. Okay. So that's my little comment. And yeah, I also added a link to this page. I don't know, some of you may have seen it in your undergrads and stuff. It's pretty popular in undergrad algorithms. If you want to visualize how these kind of simple algorithms like spanning tree and Dijkstra work, there is this site where you can go and you can give whatever graph you want, and it will show you how this algorithm executes on this graph. Okay, so it's fun to watch these animations that you get out of it. Okay. So yeah, that's something to try. But anyway, so the algorithm is the following. Okay, so it is you start with some vertex, any vertex of your choice. Okay. And let's call that a singleton set S1. And at every step, you add the smallest weight edge out of the ST that you have. Okay. Initially t equals 1, so you look at all the edges out of this vertex u, and let's say this one is the one with the least weight. You add this edge, and now your S2 becomes this vertex and this vertex. So u and v. And next time you look at all the edges out of these vertices, these two vertices, and pick the smallest one. Maybe it is this one this time, and then you add this one to your set and keep going. So that's how the algorithm proceeds. So any questions on algorithm? We did this last time, but just and the point is that these are edges out of ST. Okay, so if you are at some point where you added, let's say, these vertices, and there was a low cost edge like this, then this doesn't count. So you only look at edges that go out of ST. Alright, so we said that you want to show the correctness of this algorithm. And we said that we'll try to show this by a very structural kind of an argument. Okay, so by a very structural inductive argument. And the claim will be that at every step t, so you will show that there exists a minimum spanning tree for the full graph that contains all the edges so far. Okay. So this will be the claim that we'll prove by induction. And note that this is a strong claim. It says that, that there is a spanning tree for the entire graph that contains all of the choices that you've made so far. Okay. And this is a very common theme in proving correctness of greedy algorithms. Okay. So you say that that there is a way to complete the solution that you've chosen so far so that it is optimal. Okay? So you've chosen some part of the solution. You want to say that there's a way to complete it so that it remains optimal. So that's the idea. And so what does that mean? So we prove by induction that you say that assuming there is an MST for the entire graph containing edges added at t, we will show that there is an MST for the full graph containing also the edge that you added at t plus 1. I told you. Okay. I was going to leave this. Yeah. All right. So any questions about the claim? So this is the inductive claim that we are making. And note that at every step, this is a relatively strong property, right? Because we are saying that you've made some choices. There's a way to complete these choices so that it remains off. Okay, so let's see how you now prove this claim. So let me draw a candidate ST. So let's say this is my ST so far. And these are the edges I've chosen, and these are the vertices in ST at this point. Now I know that there are lots of other vertices outside. I know that there is some minimum spanning tree for the entire graph that contains this substructure. Okay. Alright, so now what is my algorithm doing? Right, so it is now looking at all the edges that go out like this. Maybe there's some edges here, and so on. So it looks at all the edges that go outside of ST, picks the least cost one, okay, so the least weight one. Okay, so let's assume that this edge has the least weight. Okay, so this green edge has the least weight. And let's name this edge, let's call it E. So now what is the claim that we now have to show in terms of this?
That's part of the total minimum spanning tree.
Right, so you either have to show that whatever minimum spanning tree that contained these were, I mean, you already know that there is some minimum spanning tree that contains these 4 edges, right? That is part of my inductive assumption. You can try to show that this guy was part of that spanning tree also. That would establish it, right? But you don't know that a priori, right? But you want to say that there is some minimum spanning tree that contains all those 4 and also this one. Okay, so maybe there are 2 spanning trees that that contain all of these things, but at least one of them contains this edge also. So that's what we would like to show. We would like to show now. So let's name these things so that we don't call these. So we know that and we will show that there exists an MST for the full graph, result of the full graph. That contains and also E. Okay. And of course, so now to prove this, we'll try to prove it by contradiction. Okay. So let's assume that any spanning tree that contains take any minimum spanning tree that contains E1, E2, E3, E4. And suppose it does not contain E. Okay. Then I'm going to argue that either I can modify that tree to also contain E, okay, to get a different tree that also contains E and which has the same cost, or I can come up with a strictly better tree, and that would be a contradiction, right? Because you've already assumed that this is a minimum span. Okay, so the strategy is to take a tree that you know exists. The strategy is take tree T that contains E1 through E4 and modify it to include E. Okay. So now how are we going to do this? Right? So how does this other tree look like? Right? So T is so T contains E1 through E4, but it does not contain E. Right? So if it contains E, you're done. Right? Because all you want to show is that there exists a minimum spanning tree that contains all of these things. Okay, so if it already contains, you're done. So assume it doesn't contain it. Okay, so then the tree T looks as follows. So it would have but it does not contain this edge E that goes out. Right? So, but note that this is a tree that contains the whole graph. I mean, that contains all the vertices. Right? So, this is a minimum spanning tree for the full graph. So, in particular, there must have been a path between this node and this other node. So this tree, whatever it was, it contains a bunch of other edges. So, let's say it contains some edges that go out, but it must have had a path going from U to V. So is that clear? Because this was a spanning tree, right? So the dark edges, the black edges I'm drawing are edges of tree, of this tree T. Actually, who is not clear what T is? So, okay, so some of you are not clear about what T is, right? Okay, good. That's what I figured. Okay, so T is this minimum spanning tree that was promised to exist by the inductive assumption. Okay, we said that there existed an MST that contains E1, E2, E3, E4. Okay, so that is the T that I'm considering. And I would like to show that I can that either T also contains E, in which case I'm done, or I can massage T so that by massage I mean like change a few edges here and there, so that I now include E but don't increase the cost. Okay, so that's what I'm trying to show. So is this strategy clear? Okay, good. All right, so that's what I'm trying to do. And these here are the edges of T, and it contains a bunch of others. And this is a spanning tree, so it contains a path from every vertex to every other vertex. In particular, it contains a path from U to V. Let's look at that path. And this is what I've drawn. So okay. So now this path starts off within this set ST, right? It starts off at U and ends up in V. So there must be some point where it exited ST. Right? This is a path going from this vertex U to this vertex V. Okay, and U is inside and V is outside this ST. Okay, so at some point you must have exited this set ST. Okay, and let's assume that is, and in this picture, this is where this exit happened. Note that in principle you could have come back to this and so on. So that doesn't matter. Okay, so like your path could have gone like that and then maybe hit this vertex and then come back. So you could have exited it multiple times, but it's fine. Okay, let's take at least one point where it exits. Okay. So now what do we know, right? So we know that, let's call this edge E prime. Okay, remember that we were calling this one E. So now can you compare the weight of E prime versus the weight of E? Which one is smaller? So E is smaller because by definition E was the smallest edge that went out of ST. Okay, so that's how the algorithm picked, right? So we know by choice weight of E is less than equal to weight of E. Okay, and the tree T contains E prime. Now what I suggest doing is the following. Okay, so consider a new object. Okay, consider T prime, which is T, and you remove the edge E prime and you add the edge E instead. Okay, so you take the tree T that existed, okay, remove that edge and add this edge instead. Okay, so is it clear what I'm doing to the tree? Okay, just remove that one edge and add this edge instead. And in this process, I have only reduced the cost, or at least I have not increased it, right? Because you know that weight of E is smaller than equal to weight of E prime. And I'd like to claim that T prime is still a tree. Okay, so the claim is T prime is a spanning tree. I.e., we can go, I.e., all vertices in G are still connected. Note that this needs argument, right? Because we want to show that T prime is still a spanning tree, which means still you haven't, like, by taking out that edge and adding this edge, you haven't broken the connectivity of some pair of vertices. So if some pair of vertices had a path before, you would like to say that there is a path even now. Okay, and why is that true? Can you guys see why that should be true? I mean, clearly, if a path did not involve E prime, then it was great, right? The path still exists. But what if the path involved E? Yeah, so you have.
Yeah, just because we're still reaching all of the same vertices with this path, so that with this new path T prime, so we can still construct the same tree to reach all of the other vertices.
Right, but I guess what you're saying is, if I can reach this vertex from this vertex, then basically I've preserved connectivity. Do you guys all agree with that? because the only edge I've removed is that edge. So if I can show that I can reach that vertex from that vertex, then I'd be done, because if any path used that edge, I can now instead use a different path instead of that. Yeah.
Wait, so you're saying if any path can go from V to the end of V prime, then we can prove that it's true?
Oh, no. Maybe I should name these vertices. Let's call this I and J.
But didn't we just show that the spanning tree doesn't include edge E prime? So why would it matter if we can show that I and J can be connected by it?
Oh, so the original T included Ij, right? That E prime, right? And I'm claiming that now I construct this new object E prime, but I removed the E prime and added E. Okay. This new object, I don't know if it's a spanning tree yet, but I'd like to claim that it's a spanning tree. That means everybody is connected to everybody else. And I know that everybody was connected to everybody else in T.
Oh.
Okay, and T contained that edge, right? So you have to be a bit careful. You have to say that if there was some path that used that edge E prime, now you can use some other path. And so for that, all you have to show is that in this new object T prime, there is a path from I to J. Okay. So yeah, so think about this a little while, but I'm going to write what I just said. So to show this, suffices to prove
Oh,
from I to J. Okay, and now this is clear, right? Because I removed this edge, and so now from I to J there is a path that basically is it goes around and goes. It uses E instead of E prime, and it uses all the other edges that are already in the path. Okay, so in this picture, it should be obvious to you what the path is. Okay, so and this is. Like a proof by picture. Okay, so but yeah, you can make this form. Okay. So you just use the same path that you had used from you. All right, yeah.
I mean, pictorially it makes sense in this particular instance, but are you going to go further to prove that?
Yeah. So I wrote down the formal proof in the notes. Actually, it's already there. So it's the notes for the last lecture. I just included the whole proof. But yeah. So formally, all you would do is so you assume that there was some path from U to V, right? So you know that there is some path from U to V in T. Okay, and that consisted of a bunch of edges, one of which was E prime. Okay. Now, basically, what you do is you can be formal about it. So let's say this path used edges. It went from U to, let's call this some V1 to V2, so on, up to some. At some point you hit I to J, and then you hit some W1, so on, and hit. Yeah, let's name this something. So VR and up to some WS. From this point you hit V. Okay, so I'm just naming that path. You're naming all the vertices on that path. And I'm just saying at some point you hit I, and then there was this edge ij, and then you eventually have a bunch of w's, and then you hit v. Now all you have to do to go from I to j in this in the new tree is you traverse back. Okay, so you go from I through u, and then you know how to get from u to v is an edge, and then you go all the way back. Okay. So that's what it is. So if you want to be really formal, then this is exactly. So yeah, at the end of the day, what is going on is that there is a. I mean, in some sense, there is a cycle, and if you removed one edge and added another edge, connectivity is preserved. So that's what's happening. Yeah, some of you don't seem fully convinced, so feel free to ask a question.
Question.
Yeah.
I didn't get what's the relation to the full graph here. Because outline was based on the full graph.
Right. So this path from U to V included things that were outside, right? It was actually very crucial to the argument that T was a spanning tree for the full graph, right? So I have not really used the fact that T contains E1, E2, E3, E4, right? But I don't really need to, because I just have to say that all right. So maybe what you're asking is, are you asking that I have to ensure E prime is not one of the E's? Because that I assume is clear, right? Because
No,
E prime is
what I'm asking is that what happens if you are not considering the graph?
right. So if the original T was not a spanning tree for the entire graph, then you are not guaranteed that there is a path from U to V, right? So yeah. So that's where you are using that there is a path from any U to. Yeah, but it's a good question.
So is T as minimum spanning graph?
Yeah, so that's what you have assumed. You have assumed that T is the minimum spanning tree for the full graph.
Okay, so why wouldn't it have already used E? That makes sense.
Yeah, that's what we are asking. That's what we are formally showing, right? So we are showing that if it did not already use E, then I can modify that tree a little bit to also contain E. And the reason you have to do this formally is because E prime and E could both have the same weight. Okay. And then maybe your inductive hypothesis just told you that there was a minimum spanning tree that used E prime. Okay. And but you somehow, your algorithm broke ties arbitrarily, so you decide to pick E instead. Okay. And then you might be in bad shape. Right? But what we're saying here by this argument is that that sort of thing doesn't happen. In fact, there is also a spanning tree that uses E, a minimum spanning tree that uses E. So that's another way to view this argument. Yeah.
I guess I'm confused at how we figured out that E prime really replaces E. If there's several possible edges that go out of S sub T, not all of those edges will connect to the same connected component of T minus S sub T.
So that is true, yes.
Yeah. So how do we know that that E and E prime connect to the same connected component?
So that was how I chose E prime. So how did I define E prime, right? So E prime is defined as by looking at the path in T going from U to V. T is a tree, which means that between any two vertices there is a unique path. and it's a tree, it's a spanning tree like you were saying for the full graph. Therefore, there is a path from U to V. Okay. I'm taking that unique path. That path starts inside of ST, because it starts at U, and goes out. So there has to be one edge where it leaves this set ST. Let's say you look at the first such edge. That's what I'm defining as E prime. That's what says that the general picture, in all its generality, looks exactly like this. Okay? So the only the difference could be that maybe it zigzags. Maybe it comes back to, maybe you come back from here back into T, and then maybe you go out, right? But modulo that, it looks exactly like this. So the general picture looks. So, but yeah, that's a good question. Yeah. So this is the sort of proof where you need to go look again at the proof and try to critique it and try to make sure that everything works out. Okay? But this is the basic idea. That you look at the path, define E prime that way, and then you argue that this T prime that you define by removing that edge and adding E instead is still a vector. Is still a spanning. Good. So let me leave this at this point, and then this is good because now it shows this inductive claim. And once you have this claim throughout the course of the algorithm, then once you have this claim for, let's say, P equals n minus 1, then you are done. Because then you've added all the vertices. Okay, so that's what's here. All right, so let's now look at the running time of this algorithm. So what is the algorithm again? So the algorithm was doing something like this, right? So start with S1, each step add the least weight edge out of ST. So how would you implement this algorithm if you had to do this? And how long would it take?
I'd start creating S of T or S of T, and then put exiting edges in a priority queue, and then choose the smallest edge.
Okay, so is this algorithm clear? It basically contains two things, right? So he's saying that it would have been nice if I copy pasted that, but I don't know how to do it. So right, never mind. Okay, so what he's saying is you have to maintain ST. Out of this. These are two things that you've got to maintain. And so ST is just a set you maintain, let's say, some linked list. Now, but you've also got to maintain edges going out of ST. Okay. And there it makes sense to use a priority queue because you want to pick the least edge. Okay. So let's decide to store this as a priority. Okay, and this one, let's just maintain it as a list. Not clear if this one matters. Right? Or if you really want, you can maintain this as like a Boolean array. That also takes only n amount of space, right? So Boolean array would say if some vertex is in that set or not. Okay, so think about it either way. All right, so now how do you update these things? So the update has to look like follows, right? Because let's call this u to b and endpoint b to s, and you've got to update edges going up. Of newest. Okay. So these are the steps you've got to do, right? Because in each iteration you are updating the set st, which means you also have to update the queue you are maintaining. Okay. And if you think about it, these are the steps that you've got to do. So this one's easy, right? So if you had a priority queue that was up to date, then this is just finding a min value, which you can assume is very fast. And once you have that, adding this b to st is also very fast. So let's be careful. Let's assume you've maintained. So let's say something like that. Actually, are all of you familiar with priority queues? We saw a variant of it in the first week, but just to jog your memory, so this is a data structure which just stores a bunch of elements with weights, okay, and in our case, these are like the edges. And adding a new element takes log n time. Retrieving the smallest element takes also log n time. The smarter ways to do it so that retrieving takes constant, but that's fine. We are okay with log n. And yeah, and adding and removing everything takes log n. Okay, so that's the data structure key. So right. So these two steps are easy. So now how do we update the edges going out of ST? Because what's going on, right? So here you have some ST. You've added a new V to it. So we could have had multiple edges to start with from vertices inside ST. And now once you've added V, you definitely have to add edges that go outside of ST union V. So you need to add those edges, but you also have to remove these edges from the priority queue. So suppose this one was. So you have to remove these edges and add those. Okay. Yeah.
Could we instead of bothering to remove things from the priority queue, just check when we pull something off the priority queue, check and see if it meets the constraints of the current problem? Like,
oh yes, you can do that as well. Yeah, so you can check the moment you pull something out, it's just saying, check if both the endpoints are already there, are in the same. Yes, you can do that as well. Yeah. I actually, assuming that you have this thing, both will be exactly the same. Okay. But if you had a faster operation for this, then that would actually be faster. So yeah, yes.
The thing that I'm confused about is how can E prime be larger than E?
Well, in the proof.
Yeah.
Okay. Okay, so he's asking a question going back to the proof. So it cannot be strictly larger. That's what you mean. Otherwise, you would have a contradiction to the minimality of P. But it could be equal.
Okay.
So yeah. Yeah, but if it's equal, is the difficult case. Yeah. Any other questions? All right. So this is what we do, and so yeah. So this is essentially what you have to do, and what you can show is that you can see that this operation, let's call this star. Star takes time equal to degree of v times log n. So this is what you can prove. So because some edges you've got to add and some edges you've got to remove, but they all involve this vertex v. So this is going to take time, that is degree of v times log n. So yeah, let's not spend too much time on this because this is easy. You can convince yourself afterwards. And so the overall running time turns out to be so what is now the overall running time? Yeah, so it's the sum of the degrees of all the vertices. Because each time you add one vertex and you pay cost equal to log n times its degree. Next time you add some other vertex, you pay cost equal to a degree of that times log n, and so on. So it's the overall running time is log n times sum over v degree of v, and plus some constants, right? So because these steps take some constant time, plus 1. Now what is this quantity? Sum over all the vertices of 1 plus degree of v. Sorry? Yeah, but would it always be n squared? It's definitely at most n squared.
2 times number of edges.
Yeah, so the sum of the degrees is twice the number of edges, right? So this is true in any graph. The sum of the degrees is twice the number of edges. So this one I will write it as this overall running time right here is O of log n times number of edges plus number of vertices. So this would be twice the number of edges, and these guys would just add up to the number of vertices. So that's what you have. And this is actually a very common running time. This is one of the great running times for a graph algorithm, because size of E plus size of V is the amount of space it takes to write down all the edges and vertices, right, of a graph. And that times log n. Log n is usually small. N is the number of vertices, right? So, okay, this. So this is actually a pretty great running time in terms of as far as graph algorithms. Okay, and using the kind of trick that he brought up, you can actually bring it down to O of m plus m. So it turns out that you can, instead of multiplying the whole thing by log n, you can just multiply the v part by log n if you're a bit careful and you do stuff and use a slightly more clever data structure. Okay. So yeah, so I won't get into this because for our purposes log n is somewhat small, so a slightly higher thing is fine. Okay. So yeah.
I'm missing how we changed from the sum of the degree of vertices, which we said was 2 times the size of V, or the size of 2 times the number of edges. And how did we add the number of vertices in there?
Oh, the ones add up to. Oh, this sum was actually. Okay. Yeah. Because each time you were adding a log n also, right? So yeah, and this one I just ignored it because it's much less than log n. Yeah, good one. Okay. So that's all there is. Okay, so this is reasonably simple math. Okay, so this is a general summary of minimum spanning tree. Okay, so the algorithm itself is simple, but the analysis involves a bit of work. It's still not terribly complicated, but it's this nice idea that you show by induction that there exists an optimal solution to the full problem that agrees with the choices so far. Okay, and this is a somewhat common inductive approach to greedy algorithm. So that there is an optimal solution that agrees with all the choices so far. And yeah, so this can be solved in time m plus n times log n time. M is number of edges. And one thing I was thinking of doing today, but then I thought that I'm not going to be able to do it anyway, is that this is very, very closely related to Dijkstra's algorithm. Okay, so that's why I did Prim and not Kruskal, which is, so this also ends up growing a path in exactly the same way. Okay, so we'll see this next week, but I just want to give a heads up that this is almost the same procedure, just the way you pick the next edge is a little bit different. Okay. So that's how this happens. Alright, so that's a quick summary of spanning tree. And so this is one of the basic graph problems, so that's why we all like to spend time on it. And it's also one of the basic, first non-trivial example of a greedy algorithm that works well. So that's the reason I like it. Alright, so let's now go to the next topic. And this is what I call local search. I'm not going to spend too much time on this, but I'm going to give a high level overview. So how many of you have heard of local search? How many of you think that you may have seen algorithms that use local search? Sorry? Yeah, so that was going to be my next question. So how many of you have heard of gradient descent? Right? So that hopefully all of you have heard, and so that's one of the canonical applications of local search. Okay, but this is a more popular paradigm that's used, also for other problems. And the idea is actually super simple, and it's something that you would try, which is you have a problem and you want to find a solution that optimizes a certain cost. Let's see. Okay, each solution has some cost. Now, a natural thing to try is you start with some feasible solution, and you try to improve that solution somehow locally. Right? There's, let's say you have a graph problem, change a couple of edges or something like that, right? And hope for the best. Maybe you get a slightly, for instance, you can try to do this with paths, right? Like I'm sure all of you have intuitively, at least, when you're trying to navigate, you must have seen that. Okay, if I replace this instead of going on this road, maybe I take these two roads. Maybe it's a better path or something like that. So we do this naturally also, and so you start with some solution. Don't make drastic changes to it. Try to see if slightly adapting it changes the solution. It's a very natural idea. And you declare that you are happy if there is no nearby solution that is better. So there's no clear, simple change that you can make, which makes it better. Okay, so now let's see a classic example of this. So this is where I talk a little bit about gradient descent. Okay, so yeah, and continuous domains are where this paradigm is the most natural. Okay, so let's say you have some function f. Okay, it's some function that's defined on some domain P. for the moment assume that D is some interval. So this is the real line. And let's say you have some function that goes like this. And you want to find D is your domain. And you want to find some x in this domain where f is as small as possible. Now, a natural strategy to do is you start at any x. Let's say you start here, x0, and try to move left or right and try to see where you can go so that the function value reduces. And so in this case, you will, if you start at this x0 and if you slowly follow the function, you'll end up with something over here. Okay? But instead, if you started with somewhere over here being x0, then you end up with somewhere over here. Just maybe not all. So this is it's again or maybe if you started here, it's even worse. You won't end up over here. You don't move much because you hit the boundary of the domain. This is a canonical example of function. Alright. And people do this all the time, especially for multivariate optimization. For single variables, things are easier usually. And the common thing here is something called a grid search. So you have functions of multiple variables, so f of some x1, x2, x2, xd, let's say. These are d-dimensional functions. So it takes n numbers and produces one real value. That's what I mean by this. So f maps. So this is a kind of function. And so grid search is a natural example where you start off at some point and you move left or right or up or down. And so all the neighbors have a cost that is higher than. Your goal is to minimize the function. So you move to a place where all the neighbors have a higher cost, and then you declare that that's all. This is one standard thing. And the question you should ask yourself is, when does this lead to an optimal solution? Right? So this is a natural procedure for sure. But when does this lead to an optimal solution? So the only time when these sort of procedures lead to an optimal solution is when any local optimum is actually a global optimum. So what do I mean by local optimum? Right? So it's like in this grid search example, some point x is a local optimum if the f value at this x is smaller than the f value at these 4 nearby points. That's when it's a local optimum. And so this procedure is bound to give a correct answer only if you have that nice property that any local optimum is actually a global optimum. So, and the one thing I'd like to say here is that this property is very rare. Okay, so usually functions have local optima that are not global optima, but people use gradient descent and these kind of local search algorithms anyway, hoping that they are still not very bad. And we'll see an example. We'll see a concrete example in a very different domain where the solution is not too bad. Okay. But yeah, so in general, this is not generally true. But there is one very important class of problems for which any local optimum is actually a global optimum. So, have you guys seen any such examples? Again, going back to gradient descent.
Convex.
Yeah, so convex functions are one most common example. So what is a convex function? Right. So minimizing convex function, and that you only minimize. Maximize. This does not hold for maximizing convex function. So if you want to minimize a convex function, let's say over a convex domain. In this case, I'm taking all of Rn. Okay, so f is some function that maps Rn to R. Now, what does it mean to be convex? Who wants to define convexity? Many ways to define it. That's why I asked the question, because people view it in different. Yeah.
You can calculate the double derivative of the function and show that it's always created.
Right. So the most common thing which you would have seen in high school calculus is if it was a single variable function, right? So if f was a real valued function, like and its f maps R to R, okay, so it's a single variable, then convexity is usually defined as f double prime of x is bigger than 0 for all x in the domain.
So yeah, if it's multivariable, then you need to show the Hessian matrix is
PX.
positive something.
Yeah, so right, so the other thing is if it's multivariate, so then you can define what is called the Hessian of this matrix at some point x. You have to show that this matrix is what is called quasi-symmetric. So that's is one way of saying this. But there's a much easier example, a much easier definition that you can come up with, which is that you can write that for all x and y, f of x plus y in the domain by 2 is less than or equal to f of x plus f of y divided by 2. So this is a definition that works even if f is not differentiable and so on. Okay, so this is just yeah.
What are x and y in this context?
Sorry?
What are x and y in this context?
Oh, for all x and y in the domain, this inequality should hold.
Does that hold for any number of variables?
Yes. So this is so the domain can be anything. It can be Rn. It can be anything. The only slight catch which you should notice here is that x plus y by 2 should be in the domain. Okay. So so this definition holds only for convex domain. So if I had a domain like this, then x and y can be here, but the function may not be defined at this point. So there are technicalities like this, but modulo that, this is an equivalent definition. So any questions? So this is a very simple definition that it's an alternate definition for convex. And you can also use this to conclude another thing, which is that f of for any, instead of taking the half, instead of taking actually the average, you can take any weighted average. So that's like saying you have f of t times x plus 1 minus t times y. This has to be less than equal to t times f of x plus 1 minus t times f for any. So this is another popular definition you will see of convexity. And these two are almost equivalent, assuming f is continuous. Okay, they're actually exactly equivalent if f is continuous. Alright, so any questions on the definition? All I've done is define convexity. And alright, So now what I will, so one of the standard results is that what is it? Convex function. Okay. So I've defined it over all of Rn. I mean, I can define it also on any convex domain, but for now, let's assume that it is. Then any local optimum of f is also global. Okay, so this is a it's fairly simple to prove fact, but this is one class of functions for which this happens, and it's probably the most popular. So yeah, so how many of you have seen this fact before? Yeah, so the fact you've seen it comes to. Yeah, this is actually surprisingly easy to prove, but maybe I can just do a hint and not get into the proof. Because all you have to do is you take any local optimum, let's take x, suppose it is locally optimum, and suppose there is a y which is actually locally optimum. And suppose that f of x is, f of y is strictly smaller than f of x. So this guy is a local optimum. This guy is a global optimum. And suppose strictly less than f of x. Now what you can show is that if I look at the line joining these two, and if I look at some point pretty close to x, but along the direction of y, you can argue that the value here, by using this inequality, you can argue that the value here is actually strictly smaller than the value of, so this is some x prime, so f of x prime strictly smaller than f of x. For any point on this line, you can show that this is true. And this contradicts the fact that this is a local optimum, right? Because now there is a direction very close to x where your actually value is 1. So, and that turns out to be that. So yeah, let's not do this formally, because doing formally means that we're going to some definition.
But it can be increasing function and then increasing function.
Right, that's what that definition will rule out. Okay, so if you satisfy this property, then you cannot be increasing in the middle. Okay. Yeah, that's the nice. Yeah, that's why you use the definition of convex. All right, so that's the idea behind gradient descent. Okay, so the general algorithm. So I just want to state the algorithm because it's something you do. It's basically all of modern ML, right? Like the reverse program. Ambitious, but yeah. So the general algorithm is just you start off with any some x0, and at every point update xt plus 1 equals xt minus eta times the gradient of f at x. So the only thing that I have not mentioned to you is what is one direction in which the value of f drops. So it turns out that this gradient captures exactly that. And yeah, again, let's not go into that. If I had more time, I would have spent more time on this. But yeah, I just want to mention the algorithm. So this is one classic example of local search. Okay. So Yeah, you will do this multiple times in your ML classes, so you don't have to do this. Okay, so this is data design. So now what I would like to show though are local search in some more combinatorial applications. Okay, so let's see one very simple example of that, and this is what I call the matching problem. Okay, so you guys may have seen some variant of this, right? So you have some n children and you have n gifts, and each child has some happiness value that he or she gets if the child gets that gift. So it's formally it's some kind of a weighted bipartite graph. So you have children on this side and gifts here. So let's call these C1, C2 to Cn, and G1. And the valuation that child I gives to gift J, I will denote by VI. This is like a happiness value. And your goal is to assign gifts to children so that the sum of all the happiness values is maximized. Okay. So this is a very natural problem, and of course you want to give only exactly one gift to each child, and assume also that these B's are all non-negative and so on. Okay. Any questions about the problem? So this problem will keep coming up, so it's good to understand.
How maximum happiness happen?
Sorry?
How maximum happiness happen? You want to maximize the happiness.
The total happiness, which is the sum of the happiness values of this assignment, right? So if I give, yeah, it's a good question. So if I have three, 1, 2, 3, and gifts 1, 2, 3, and if I give gift 1 to child 2, gift 2 to child 3, and gift 3 to child 1, then my happiness value would be something like V13 plus V21. So this would be the cost of that solution. So that's just an example. Okay, and I'd like to find, I'm given the happiness values Vij for every gift for every child. That's the input. And you would like to find an assignment so that this kind of the total happiness is as large as. Okay, so now when you see this, I guess the natural instinct is to come up with a greedy algorithm for this, right? Like how would you try to come up with how would you try to do this matching if one were to give you this problem? Yeah?
I will take every child and look at all the happiness value associated with it and take the maximum.
Right, so this is a good solution. I mean, it's a very natural solution, right? Like you have all the children, go in some particular order. Right? So you say, okay, I look at children 1, 2, 3, 4 in that order, and for one, I first give the gift that this person values the most, and maybe I give this gift, and then I go to 2 and do the same thing. But of course, I cannot give the same gift to 2 people, so I only look at the like the gifts that are still remaining. Of those, I pick the best one, and so on. But you can easily imagine that the ordering really matters in this, right? Because I mean, in some sense, you decided to go in this order 1, 2, 3, 4, but you come with an example where, let's say, one had, even with just 2 gifts and 2 people. So if 2 valued a gift 1 to 10, This one was the weights were something like 1, 2, and this one was let's say 1. In this case, if you went in order 1, 2, then you would associate. I mean, you would give the second gift to child 1, which is not great in terms of maximizing the total happiness value, because in the end you care about the total happiness value. So greedy will not work. Okay. So is this example clear? Okay, so it's you just have two children, and these are the happiness values. You start with 1 and give the gift and give it the most valuable gift for that person to that child, then you lose this very high value of happiness that you care about. Yeah.
Would it work slightly better if, when we're being greedy, instead we consider edges, we choose the lowest edge that's not like trying to set?
Right. So you can try doing that, but yeah, again, you can find counterexamples to that as well. Yeah. Yeah, but that's a good suggestion. So you can try to say, well, I'm going to go by the edge weights and try to pick the best edge where both the endpoints are unassigned. Yeah, and make that assignment. So yeah, so that also is not optimal. And in fact, for these kinds of algorithms, actually, I think even for that algorithm, you can show that there is no very good bound you can get. Actually, for this algorithm, it's trivial to see, right? I could have made that 10 equals 1,000. So there's no way I can even compete in terms of some kind of a multiplicative approximation to the optimum or something like that. So in this case, it does not work well. It can actually be arbitrarily balanced. Alright, so now for this problem, I'd like to come up with, let's say, a local search approach. So in this example, right? So you can imagine that after you've made your greedy assignment, you can go back and see if, maybe instead of giving this gift to that and that gift to this, if I had swapped the gifts, it would have resulted in a much better solution. So can you now come up with a local search approach for this problem? Yeah.
Maybe almost doing what we used to be a then check for the neighbor or for the children that close to the specific children, and see if we switch the gift and give it to that specific children. Is that going to give us a bigger happiness value?
Right. So you start with. So this is the main thing in local search, right? You start with some full solution. Right? So you start with some assignment. So let's say I have an assignment that looks like this. Let's be a bit more. So let's say I start with some assignment like this. Now what do you want to do?
After doing our assignment, the first thing, we will check neighbors and see and compare the happiness value and see if we can
What do you mean by neighbors?
Oh,
you mean like two next to each other?
For instance, yeah.
Okay, so what you're suggesting is, so look at some pair of children
that's close to each other and see if we switch the gifts, if this is going to give us a better happiness values.
So, right. So now let's look at children 2 and 3. What he's saying is that 2 was given, let's say 5, 3 was given 2. So now instead, keep all the other assignments the same, but now give 2 to 2 and 5 to 3. See if that improves the situation. See if and he's suggesting doing this only for pairs that are nearby. But there's no real, there's no real reason to just restrict to pairs that are nearby, right? I mean, there are only n squared pairs of children, right? Like you can try doing this for every ij, right? So candidate local search. Is for every pair I change. Okay. Try to see if improves the cost, improves total cost. Okay, just out of curiosity, so how long does it take to do this check? Yeah, n squared, because you have to do this check, and of course each time it's just constant time, right? You just swap and you see how much because all the other assignment stays the same. It's only, that's why it's called local search. You only check if changing the solution for two children improves the value. And if so, you do this and you restart. So the next class we'll see how this very, very basic algorithm results in a solution that's not too bad. Okay, so formally what we'll show is that you take any solution in which none of these like pairwise swaps improve the value. You can show that the total happiness of that solution is at least half the total happiness of the optimal solution. Okay, so this is similar to this algorithm that we saw for set cover, right? Like even though this is not optimal, this results in a solution that is not too bad. And this could not have been said of the greedy algorithm, right? Because the greedy algorithm, like I can make this 100 equal to like 10,000 or something, and the ratio would blow up. So that's what we'll show next time.